Next, we have Lorrayne Miralha, who we see here, and she worked on a project this summer with Regan Errera and Jim Hood, who's from Ohio State University. And we're excited to have Lorrayne here this morning to tell us about her work.
Perfect. Just to confirm, is it in the notes one or just like my slides?
We see your slide and presenter view, so everything is good to go.
Okay, perfect. Thank you.
Wonderful. Thank you.
Okay, hello everyone. I'm Lorrayne. Thanks, Mary, for the introduction. And I'm a summer fellow with GLERL this year, working virtually with Dr. Regan Errera from NOAA GLERL and Dr. Jim Hood from the Ohio State University. So Lake Erie, one of the most productive of the Great Lakes, providing crucial ecosystem service to the region. It supplies water for more than 10 million people, and it's essential to agricultural, industrial, and recreational activities. Due to the development in the region, eutrophication symptoms appear in the system. And this is not new to Lake Erie, because back in the 1900s, eutrophication was an issue and management strategies were applied to ameliorate this problem. However, eutrophication is back, including hypoxia and harmful algal blooms, concerning us as scientists, agencies, and the public. So HABs are part of one phytoplankton major species that can release toxins, disrupting food webs and impacting human health. Therefore, understanding how these algae species behave is important, principally in order to alert society about the conditions of the water they use daily. Okay, so several factors can control the dominance of algae species in freshwater ecosystems, such as climate, nutrient inputs, and the presence of other species as well. Here is a hypothetical phytoplankton successional sequence in the top layer of a temperate lake with some stratification, and we can see that classical shift from a diatom-dominated community to a cyanobacteria-dominated, primarily controlled by silica and phosphorus present in the system. In eutrophic systems such as Lake Erie, this phytoplankton species would tend to concentrate mostly in the spring to fall season and controlled by both physical as well as nutrient characteristics. In order to understand how these shifts occur, recent studies worldwide on phytoplankton dynamics have focused on understanding the ecological conditions or thresholds driving the dominance of one phytoplankton species over another. These thresholds have still yet to be investigated for Lake Erie. So this summer, the main question I was interested in answering together with my mentors was to what environmental threshold conditions influence this phytoplankton assembly shifts over time and space. I pulled up 2 Sentinel satellite images from the same month and week, but different years, in order to understand the spatial temporal pattern of phytoplankton species. And here we can see that at same location, over time, the spatial patterns are different. So what is happening here that is not happening here in the following year? So Western Basin of Lake Erie, where this is the focus of my study, and this Western Basin receives flow from 2 main rivers, the Detroit, which contributes around 80% of the total inflow for the Western Basin, and the Maumee, responsible for less inflow, but also for the highest amount of nutrients entering the lake system. In order to monitor these inputs that are major drivers of harmful algal blooms, NOAA samples more than 10 sites weekly during the spring to fall season. But in this study, I focused on major 4 sites with consistent data from May to October, as you can see here in the map. The data used consists of chlorophyll A concentrations per phytoplankton groups, such as cyanobacteria, cryptophyta, diatoms, and chlorophyta, which the measurements were just possible because of an equipment called fluoroprobe that NOAA owns. The water quality variables database I used was the NCEI, which is composed by variables such as nutrients, water temperature, and so on. And mainly, this data goes from 2015 to 2019 during the spring to fall season, which is basically a proxy of the measurements of the fluoroprobe. So here I will guide you through all the questions I attempt to answer, the analysis I use, as well as my results. So first, what variable can best explain phytoplankton biomass? So to answer that, I use correlation, principal component analysis, as well as discussions with my mentors about what would be the most suitable variables for modeling the dynamics we are interested in. I ended up with 9 variables among around 40, and these variables, to not lose information of like very high correlated variables such as nutrients and organic nutrients, we calculated ratios such as CN and NSRP for the system. So here, these variables were the variables selected, and mainly represent the conditions of the lake, the most important nutrients, as well as water temperature. Now, we wanted to understand how these 9 variables relate to each phytoplankton group. To answer that, I use a redundance analysis, which extracts the variation in a response variable, in our case, the phytoplankton groups here in red, and explained by a set of explanatory variables, which are in blue here. After several runs, we observed that the most significant RDA components, the redundance dimension components, were driven by turbidity, SRP, dissolved oxygen, NSRP, and temperature. So these explanatory variables correlated differently with each phytoplankton group. For instance, here we can see the cyanos were mostly related with turbidity and temperature, but very weakly correlated with SRP. This might be associated with the fact that available phosphorus was gone in the system. Cryptophyta was negatively related with SRP, but positive with temperature, while diatoms were associated with SRP, GO, and NSRP concentrations, while chlorophyta mostly with NSRP and dissolved oxygen. Here we come to the third question, which basically relates to the importance of these variables and how to determine each phytoplankton group concentration and how it's influenced their dynamics in the system. So using regression trees, I modeled each phytoplankton group concentration, chlorophyll A concentration, with the 9 variables I previously showed. These trees illustrated different phytoplankton lake conditions dynamics, and noting that the first split here of each tree determines the following splits, and therefore will be the most important. From the red color illustrates the highest chlorophyll A mean concentration, while the darkest blue are the lowest mean chlorophyll A concentrations per each phytoplankton group. So for the cyanos, turbid conditions drove the highest concentration of this species in the system, with temperature higher than 25 Celsius and SRP influencing these concentrations, but not as the first most important condition. For cryptophyta, temperature was the determinant factor. However, in a threshold lower than the one saw for cyanobacteria. And here we clearly see as well that nitrogen starts to play a role in determining the highest and the lowest concentration of this species in the system. Not only ammonia, but as well as NSRP. For chlorophyta and diatoms, the tree showed up to be more complex with several splits. And here we see that NSRP as well as SRP are driving chlorophyll presence with highest concentrations when temperature also higher than 24 Celsius. For diatoms, the most important conditions were dissolved oxygen, followed by nitrogen compounds. And this analysis clearly showed that and give us insights about what specific conditions each species are likely to dominate. We proceed and try to determine the split value for each one of the groups using the first splits of the trees. So here, the primary environmental factor was based in this first split of the trees, and it differed for each phytoplankton group. So for cyanus, turbidity was the most relevant factor. For cryptophyta was temperature. For diatoms, dissolved oxygen, and chlorophyta, NSRP. So now we want to detect the threshold of these parameters for all groups to get more insight on their dynamics. And to do that, I use the change point analysis, which is basically a detection of thresholds using a segmented regression approach. So for the turbidity parameter, we saw that cyanus are mostly dominating in turbid conditions, followed by cryptophyta, and this higher turbidity may be connected to the higher biomass of cyanus in the water, while diatoms and chlorophyta are mostly likely to decline in these conditions. For temperature, we see that diatoms and cryptophyta enjoy cooler waters compared to cyanus and chlorophyta that show to be able to hold in very high temperature conditions. Principally chlorophyta that starts to show up in the system when cyanus start to decline. Concentrations of all species, with exception of diatoms, decline when we have dissolved oxygen higher than around 7.5 milligrams per liter. And here we see that diatoms are really comfortable with high dissolved oxygen conditions. This was the first most important split for chlorophyta. And this analysis showed that when this ratio is very high, cyanus are more likely to be present in the system, basically because available phosphorus is probably gone in the system. Other species decay when this ratio increases, but chlorophyta resist in higher ratios compared to diatoms and cryptophyta. So how these thresholds hold and help us understand the spatial temporal patterns seen from 2015 to 2019 in the bloom season. There are several ways of doing that, but this is just a simple way of visualizing it, and much more can be seen when we compare all the years and the stations. So let's dive in. What we see here is, and the question we can answer is, why in the station 2 we see a dominance of diatoms in 2019, and in the same period in station 4 we see a dominance of cyanobacteria. That can be explained with the four most important variables we found with our regression trees. Basically, in the station 2, while dissolved oxygen mean concentrations were around conditions that all species would be present in, it did reach concentrations that diatoms were comfortable with, and as well as temperature were lower. While for the station 4 in the same year, water temperature were really high, conditions that only cyanus or green algae would be dominating, but dissolved oxygen was lower than usual. So that helped the dominance of the cyanobacteria in this site. For 2019, we observed the dominance of green algae in the station 4, and we saw with the trees that their dynamics are more complex. So observing all the the four most important variables, we see that GLERL concentrations were around the threshold we found, while temperatures reached like high values, but turbidity conditions were lower. But the most important factor was the NSRP ratio that became around the 90 ratio value that green algae would be most likely to predominate. So to sum up, this summer I worked on understanding phytoplankton dynamics and the interaction between phytoplankton and environmental conditions. We saw that this analysis showed that cyanus were most likely to be related with turbid conditions as well as high temperature waters, while diatoms seems to be determined by the presence of dissolved oxygen, high concentrations of dissolved oxygen in the system. Cryptophytes show to be similar, to be present at similar turbid conditions as cyanus, but in lower temperature locations, while chlorophyte dynamics as well as diatoms were more complex and their concentrations were more related to nitrogen in the system. Which is interesting since most of research have focused on the phosphorus presence. Therefore, here we also highlight the importance of nitrogen compounds in phytoplankton dynamics. These results I have shown here may serve to advance or develop models used to predict phytoplankton biomass and consequently help guide management strategies for the region. And this study also shows the potential of fluoroprobe measurements on investigating these dynamics. And even though we still did not calibrate the fluoroprobe measurements in this study. I thank you all for this opportunity. I thank my mentors, Regan and Jim, for their patience as well as expertise, Ziegler, especially Mary and Michelle, and all of you for making us feel welcome in this virtual environment. It has been a wonderful and productive summer. And I thank also my PhD advisor, Dr. Rebecca Munich, for all her support as well. Thank you.
Thanks so much, Lorrayne. Fantastic job. I loved your presentation. You did really well.
Thank you.
We have time for questions, and we've got a couple of things here in the question box. So first, Regan, one of your mentors, says, it was a joy to work with Lorrayne this summer, and I can't wait to keep the collaboration going. So I know you'll I've heard from, I think, both of you that you're going to work on a paper yet this fall, and I think that's super exciting. We love to see when fellows and their mentors keep in contact, and if you can get a publication out of your work, that's just fantastic. Hank Vanderploeg from GLERL asks, is the turbidity associated with loading or wind stress?
Okay, that's an interesting question. Thanks for that. So the turbidity at the beginning of the season, it's mostly likely to be driven by the loading coming from the Maumee Basin, and that's something that we are trying to account for to separate the abiotic and biotic factor. So it's mostly like that. It is related to the sediment coming down from the watershed.
Okay.
As well.
Thanks. Yep. Thanks, Lorrayne, for that answer. We'll give it a few more moments in case someone has another question or if Hank has a follow-up on that. Hank says thanks, so that must have answered his question, and thanks for asking that, Hank. Okay, I'm not seeing anything else come through. So Lorrayne, thank you so much. And again, I say this every time, but if people have more things that come to mind, feel free to type them in, and Lorrayne can address them later on during this session.